Oh, I didn't finish this page. All right, so what's an algorithm or code? We often refer to them as machines. Why? Because we're dating back to Turing, and Turing called them Turing machines, right? That happened before we had code. So we often call them, we also use M for machine, but it's just code, right? In fact, whenever I say Turing machine, you have a choice. You can you can panic and think about this course, or you can think, oh, he really just means Java code, right? So what is Java code? Well, the key is that it's described by a finite list of instructions, right? It's described by a finite string, and given an input, you follow those instructions based on this string. You follow those instructions, and in the end, it will do one of two things, right? It'll either run forever, which then there's not really an end, right? It'll either run forever, or it eventually halts and outputs something, right? Everybody understand what that is? So here's an example. The problem could be sorting, and the algorithm could be insertion sort, which amusingly enough we just covered in 3101 10 minutes ago. All right, so now let's try to understand how we're going to write certain things in first order logic. And remember, the reason I'm so big on writing things in first order logic is because we're going to have to prove things. And how are we going to prove them? Is we're going to follow the first order logic game. And if you don't really know what we're trying to prove, i.e., you can't write it down in first order logic, how are you going to ever prove it? Right? So we want to say problem P is computable. And how do we say that? We say there exists a machine that can compute it. Right? And what does it mean to be, oops, where did we go? Oh, we went somewhere really bad. I hate those buttons. Can you fix those buttons? We can pull off the keyboard the button that makes you go to the end. All right, so here, what do we want to say? P is computable if there exists a machine, an algorithm, that computes it. Right? That's pretty straightforward. And, here this is a very simple exists, right? Because an M is just a finite string, right? It's described by a finite string. It's described by Java code. So here we're saying there exists some Java code that computes P. Right? So now we have to see, what does it mean to compute? What we mean is for every input, right? What does it do for every input? It gives you the right answer, right? And what's our input? Here we're thinking about, another thing I didn't tell you about inputs is they're all finite, right? It could be a binary string, or it could be an elephant. They all have a finite description, right? So again, we're just doing a for all over finite integer-like things, right? And now we need to say, does this Turing machine solve this problem on this input? Right? So we write that down. And here it's just straightforward. M on input I gives you an output which is the same as the problem on input I. Right? And you might notice I slipped under the rug a subtlety, and this subtlety is going to be scary when we start proving things like the halting problem. Anybody know what the subtlety is? M might not halt. Right? And so what does this mean? And you could say, well, it means infinity. It could mean it outputs panic. It could mean it outputs whatever you want, right? But whatever you're outputting, it's not this, right? So this, if M's not halting, then this is not true, right? Everybody buy that? So this is basically saying M halts on I and gives you the right answer. Right? Everybody good? Yeah.
But I'm kind of confused because all you're doing is stating that there exists a machine.
Right. Right. Yeah, so we haven't proved it yet. Now we're just stating it. You're right. And what I think you're referring to is when I was trying to motivate stating it. Why do we need to state it in first order logic? It's so that we really know what it is we're saying, so that later when we prove it, we know what game to play. Right? I mean, how would you prove this? Right? In fact, if it's not next slide, it's going to be soon. Right? How do I prove there exists an M? I give you an M. Right? Here, P could be sorting. How do I prove to you that sorting is computable? Well, I give you a machine. I give you selection sort. The adversary gives me an input. Right? Let I be an arbitrary input. Right? And then I have to prove that my algorithm solves sorting. Right? That's the way we've always done it. In fact, here it is. I knew we were going to do it. Right? Let's play the game. Here's the proof. Right? Right? We have to do exists. We read from left and right. When it's an exist, it's my job to come up with the thing. So I can say, I have a machine that solves the sorting. Right? And then the adversary knows my algorithm. Right? Because different algorithms, some algorithms work on some inputs and some algorithms work on different inputs, right? He knows my algorithm and he's going to come up with an input in which my algorithm doesn't work, right? And then we have to prove that my algorithm does in fact work on this input, right? And what is P? What role does P have? P is a free variable, right? So whether this is true or not depends on P. If P is sorting, it's true. If P is the halting problem, it's false. Right? Everybody got that? Right? This is what you do in computer science, right? Nothing new here. All right, so what are we doing? Right? It's just, let's talk about, you probably heard the terms compile time versus runtime, right? So we're going to be using that concept often here. Compile time means what? You know the machine, but you don't know the input, right? Runtime is when you know the input, right? So that's what we're going to mean by what do I know at compile time? What do I know at runtime? Right? So that's what we're going to talk about here. Right? Exist M, right, is what I know at compile time without knowing the input. I need a finite description of the machine, right? Finite set of instructions, finite set of variables, right? Each variable has a finite range, maybe, right? Now, the input is at compile time, is at runtime. Right? At runtime, I know the machine and I get to choose the input. Right? And I could choose the input to be much bigger than the machine. Right? And so what do you need in the computation? So let's go back to, say, 2011. Remember the data structure course? We set up our code at compile time has a bunch of pointers, right? References. And then, and how many pointers do we have? We have a fixed number of pointers. And what can they do? They can just hold a value, right? Now, what do we do during runtime? Runtime we can call, I'm going to say malloc, but that's C. What do you do in Java? You say new, right? You can say new as much as you want. So here at runtime, we can dynamically allocate more and more memory, right? And here I'm helping you warm up to the idea of what is a Turing machine. Because the Turing machine is going to have a finite state automata, which is what it knows at compile time. And then it's going to have an infinite tape that it uses during runtime. All right? Everybody kind of buy this? And the amount of time can depend on the input. Right? At runtime, you can use as much. I just am claiming that it halts. I didn't say when it halts. Right? The bigger the input is, the longer it can run. Right? Everybody following here? So, and P, as I said, it's a free variable. So whether it's true, it depends on what we plug in there. So now we can talk about P being uncomputable. All right? And I have, I could get you guys all to think about how do we write down it's uncomputable, right? And I've queried people and I've gotten lots and lots and lots of wrong answers. All right? This one here, computable, is pretty intuitive, but the uncomputable is not intuitive. And so if you want to know some wrong answers, if you haven't noticed, all my slides have a slide that says end, and then everything after it are things that I haven't wanted to delete because I made them at one point, but we don't cover in the course, right? And I think down there's some bad examples of this, all right? But how are we going to get our statement here? We're not going to use our intuition. What are we going to do instead? We're just going to invert the quantifiers, right? If we want to take the negation, we just invert the quantifiers, right? People struggle with it. Their intuition tends to be wrong, right? So you need to be able to prove things. You both need to do things mechanically, and you need to bring some intuition. And here, intuition fails. So let's just take the negation, right? And here, right, if it's not true that there exists a machine, then for every machine fails to compute, right? And what does it mean to fail? To compute, you have to get the right answer for every input. To fail to compute, you just have to get the wrong answer on one input, right? One counterexample. And then it's got to get the wrong answer. So how do we prove a lower bound? I mean, we call this a lower bound. We prove you can't do something. How do you prove a negative result, right? For that, we have to say the adversary gives us an arbitrary machine, right? Now, what do we know about this machine? All we know is that it has a finite set of instructions and that it's going to run. We don't know what it does, right? But based on that, we're going to have to then do what? We're going to have to come up with an input, right? We're going to study this machine, and we're going to come up with an input, right? And then we're going to prove that that machine, what does it do on the input? Do we know what it does? What does this machine do on this input? It fails, right? And how can it fail? It could either run forever, or it can halt and give the wrong answer, right? Yeah?
So here you say all machines there exist, for all machines there exist some answers where it's false.
Mm-hmm.
Does that mean there is some answers, some inputs that make it true, or can you not assume that?
I'm going to go with yes, but hold that question for a minute. We're going to get that in a slide or two. Yeah?
So how do we know forever in terms of time? Maybe it just takes like really long.
Very good intuition, right? So I think let me interpret your question. You're asking, how do you know whether or not your program is going to halt?
Yeah.
Right? Because what do you do to know if it halts? You run it, right? And you run it for a while. You run it for a million years. If it halts, then you know it halts. But if it doesn't halt, you don't know. And that's why hold that question for 1 second too, because that's going to be on another slide. And I'm not sure which of you are going to get your slides first, but they're next, definitely the next and the next slide. All right? So, right, so proving this is hard. Yeah?
So my question is, right now we're saying there's a machine that can handle all the inputs for computer ability.
Yes, here there's a machine that handles them all. Yeah.
Okay, so can I have a machine that handles some of the inputs, but there are other machines that can handle the rest of them? Is it still computable? Like, can there be different algorithms or different machines?
If there's a meta machine that, given an input, knows which machine to run, then there's a meta machine, right? I mean, the meta machine might say, I'm going to run. In fact, how we're going to prove these things often is we're going to say, well, if we have a machine for these inputs and these inputs, now I'm going to get a machine. I'll run all those machines in parallel, and if one of them gives me an answer, then I'll be done, right? But that's still a meta machine. Does that answer your question?
Yes.
All right, so now let's see which of you are going to get your answers first, right? So here we got the halting problem, right? The halting problem is simply the input is I give you a machine and an input to you, and I ask you yes or no, does it halt, right? Easy question, right? Does it halt? But we already gave the intuition that we don't know how to know that, right? The intuition is all we know how to do is run the thing, right? And we only can run it for a finite length of time, right? So how can we know? And that's what this is saying. The halting problem is uncomputable, right? We are going to prove in this class that, I'm promising to cut out hard proofs, but this one is so nice that we won't cut it out, right? We're going to prove that you give me any Turing machine, I'm going to give you an input to that Turing machine in which it doesn't know how to solve the halting problem, right? Versus over here, clearly, sorting is computable, right? Everybody good? Now, let's ask a different question, and that's going to be addressing what the other man asked, right? Here's another statement in first-order logic. And I'm hoping now that all of you know whether this is true or not, right? But so far my experience is nobody ever knows. So study this. For every input, there's a machine that solves the problem. Right? Well, we know halting problem is undecidable. So we all want to say no, right? You want to say no? He doesn't want to say no, right? Is it what I want to teach you is maybe what we need to do is every time you see, like Clockwork Orange, did you see that? We'll put little things under your eyes and we'll show you statements like this. And when you see ones that are wrong, we'll give you drugs to make you feel uncomfortable. So, because what I want is when you see something like that, I want you to have a visceral body reaction that this is horrible, right? We don't want every input to have its own algorithm, right? We don't want that. So I'm not going to embarrass you to ask you whether this is true or not. Let's just play the game, all right? I'm claiming it's true, right? Why is it true? Well, play the game. So the adversary has to give me an input, right? So now I have a fixed input. Now what's my goal now? Is my goal to come up with the Turing machine that solves the halting problem? No. My goal is to come up with a Turing machine that gets the right answer for this input, right? All right, so let's think about it. I'm going to tell you two. So on the input I was given, either the halting problem, it's a yes-no problem, right? So either it says yes or it says no. Do I know which one? No, because I don't know how to solve the halting problem, right? But I know that it's one of those, right? All right, if it's one of those, I'm going to come up with two algorithms. Here's Turing machine yes. What does Turing machine yes do? It says yes. Turing machine no It says no on every input. Now, I'm claiming that one of these algorithms does what we want it to do. Right? But one of these algorithms, it gives the right answer. I don't know which. Right? But I know that one of them works. Right? I don't know which one works. Everybody got that? The point is, every input has a machine, namely one of these two, that gives the right answer. Right? Everybody good? All right. So, all right. I don't know what we're doing. Oh, here I'm basically grabbed the slides. I forgot that I put this in here. Much later, in maybe the last day of the course, we're going to prove Gödel's incompleteness theorem, which is a beautiful thing that given any finite proof system, you can't prove everything, right? And in order to prove that, we could be a logician like Gödel, or we could be a computer science person. And since we're the latter, we're going to reduce it to the halting problem. And to do that, we want to be able to say, we're going to write down in first order logic the statement that M is a Turing machine that halts on input I, right? And how are we going to do that? Well, so we need to prove that M is a fixed Turing machine that we have in our hand, right? And I is a fixed input that we have. They're both, and now we're going to write down a first order logic statement that it halts. So what are we meaning by it halts? We mean that there's a halting computation, right? And all we're saying is there exists a halting computation. And one of the things that's true about halting computations is that we can describe them by 0-1 strings that are a finite length, right? We just describe what does the computation do. And any finite string we can describe by an integer, right? So we can encode the computation by an integer c. So here we're saying there exists an integer c that's encoding the halting computation. Right? Does that make sense? This is the kind of trick that us theory people do all the time. In fact, you might have heard the word Gödel numbering. I don't know if you learned about Gödel. This is a Gödel numbering. All right, so anyway, what do we want to say? We want to say there exists a computation for which, such that for every time step, the Turing machine is taking a legal step. Right? So we have it for all time. And then, now, when we're later on, we'll do this. But right now, it's just how do we show in first order logic that computation C is taking a legal step of Turing machine M on time step I. Right? We have to sort of work that out. Everybody kind of good with this? Anyway, that's all you're going to get. It was just a warm-up for the types of things we're going to do in this course when it gets really scary. All right? So now, let's talk about time complexity. Right? What does it mean? Before we were saying a problem is computable. Now let's say that it's computable in time n squared. Right? We already did big O, but I'm going to drop the big O now because that just makes it scarier. Right? Let's say that we want it to be computable in exactly n squared time. Right? What do we want to say? Right? Here it is. We're going to say there exists the machine that for all inputs, the machine is giving the right answer, and the running time of this machine on this input is at most the size of the input squared. Right? Does that make sense? Right? People might say, well, why don't you put n squared here? Well, I don't know what n is. I could add that n is the size of the input, but I just stuck that in there. Right? Are people following this? Here's a first order logic. Right? So how do we say it's not computable in n squared time? Right? Here's some things that are wrong. Right? We could say for every input, if it solves the problem, it takes too much time. We could say for every Turing machine in every input, if it gets the right answer, it solves the wrong time. Right? We could write down various things. right? Yeah.
Why is the second one not true?
The second one? This one? It's not true.
Like, can not all machines can solve all inputs? Is that what it is?
Um,
The first one is false. So false implies true is false.
yeah. Yeah, certainly for every... This says it kind of makes sense. For every machine, if it solves the problem, then... Right, but we're not talking for which input, right? So that's not really clear. So here we're saying if it solves the input, right? And so then this, I don't know, let's not get into that. I don't remember. That, right? They're not right. And we could come up with counterexamples. Again, we're just going to take the negation, right? So what's the negation is this. All right? So we flipped the exist and the froze. We made this a not. We made the and into an or. Right? And we made less than into greater than. Right? And so how do you prove this? You say, well, let n be an arbitrary machine. Now I come up with an input. And that input, either it gives the wrong answer or it runs too long. Right? Everybody follow that? So this is how you say P is computable in polytime. This is how you say P is not computable in polytime. This is how you say P is computable in exponential time. This is how you say P. Here, now we're going to say the class of computational problems called exponential time. What is exponential time? It's the set of all problems that can be solved in exponential time, right? What is polytime? It's the set of all problems that can be solved in polytime. And we're going to say that the one set is bigger than the other, right? Strictly bigger. What do we want to say? If one set, let's draw a picture. Here's P. Here's exponential time. I want to clearly anything that we can solve in polytime can solve in exponential time, right? I mean, that's... So what do I want to say? I want to say this set is bigger than this set. What do I want to prove? Right? One thing that always... You got to differentiate between poly and a problem. That comes up a lot in my life. But we want to say there exists a problem, right, that can't be solved in polytime and can be solved in exponential time, right? So I'm just trying to give you a flavor that most things that we want to say in computer science we can write down as a first-order logic, right? And then, how would you prove this? Well, you have to come up with a problem, and then you have to prove that for every machine there exists an input which it gives the wrong answer, and you have to give me a machine that's for every input it gives the right answer. Right? That's how you have to prove that. And it's good to know how to prove these things, right? All right. So, I had a test for this course in which I was asking these questions, and again, way too many people got it wrong, right? What we're going to be asking here is, can we translate the concepts that we're learning in this course, can we translate them into first-order logic so that we know how to prove them, right? And the question was, can we? And the answer was, no, most of you can't. All right? So here's an example. Remember, you all put up your hand that you swore on whatever you swear on, that you would put up your hand if you didn't understand something, right? Or you can just sort of shake your head and hopefully I'll notice you, right? Or if you're following it, do something. Do something, all right? So here, really, I want you to understand what we're doing here, okay? And, you did ask me that one question and I bailed on you, but, generally I won't bail on you. Yeah, I was curious too. And let's think about it again. You know, I'm in the subway. I can think, oh yeah, I had counterexamples for that one point. But let's try to come up with, you know, you're trying to, you know, what are we trying to do there? We're trying to come up with an example where this definition doesn't really capture what we mean, right? So anyway, right, let's do some first order logic here. What do we got? We got P is a computational problem. K is going to be an integer. A, I'm using A here instead of M. I don't care. It's either a machine or it's an algorithm, right? It's a Java program. Sometimes I use J for Java. I is an input string. Here, we're talking about how many... All right, so this is a tricky one, right? The tricky one, it's going to be the number of lines of code describing the algorithm when you have input I, right? And you might all be screaming, well, the number of codes you have on the algorithm doesn't depend on the input. Well, that's the kind of thing that we want to say in a first order logic statement, right? So save that and we will write that down, right? But we need to be able to write that down, that the length of code, the length of the code of the machine doesn't depend on the input, right? We're going to write that down. Right, so anyway, here it gets the right answer, and now we're going to come up with some first order logic statements. All right. So here I'm just going through it. Computable, right? Number of lines doesn't actually depend on the input, right? These are types of things we'll say when we were, you know, I don't know what. All right. So here. I thought I was going to give you meaning, and you had to come up with first order logic, but it seems that we're doing the reverse, right? I'm going to give you a first order logic statement, and you're going to tell me what it means, right? That was the ramification. What does this mean? And when I ask you, what does it mean, and you write down, there exists a case, it's that for all A, you'll get a 0 for that, right? You got to get some actual meaning here. All right, so let's think about it, right? Again, we could start from the inside and work out, right? For the inside, it's we have a bunch of free variables, right? We have K, A, and I. Or now, if we're ignoring that, then those are free variables. And what are we saying? We're saying, well, the number of lines of code in algorithm A when the input happens to be I is K, right? And A on input I is giving you the right answer, right? That's what this all says. Everybody agree with that? Now, let's bring in the for all inputs, right? Ignore this. We still have a fixed K and a fixed A, but we want to say, what does this say? We want to say it doesn't matter what the input is, right? I can even not mention the input. I can just say algorithm has K lines of code. And as a subtext, I could say for all inputs, the inputs don't matter, right? And here, I could say algorithm A gives me the right answer to problem P. And as a subtext, I could say that's true for all inputs. It doesn't matter what the input is, right? So people, how are we understanding what this says? So this is exactly what I said we were going to say. So now we know this. Now we can bring this in. What is it saying? Well, we're saying there's some algorithm that has the property, right? There's an algorithm that has K lines of code and solves the problem, right? Now, but we don't know what K is. So this is saying, again, it's saying there's some algorithm with some number of lines of code. It's just saying there's an algorithm with some number of lines of code. And the number of lines of code is always the same no matter what the input, and it always solves the problem no matter what the input is. Right? Does that make sense? And so this is saying this is true. You have to know whether it's true. The algorithm, here was my answer. I'm saying it's true. The algorithm designer can build an algorithm with some number of lines of K. It gets to choose the number of lines of K. And no matter what input is, this algorithm will solve the problem, and it will always have this number of lines of code. Right? People buy that? Are people following this? Yeah?
So that's the kind of way you want us to translate any given sort of logic?
Yeah, you want to give me some sort of meaning here, right? And I'm sort of, I'm almost incorporating in the game of who gets to do what, right? There's the game of the algorithm designer, right? Who's that? That's the person who there's somebody who gets to choose the algorithm and the input. And the point is that the algorithm designer gets to choose any algorithm and gets to choose any input. It's really the algorithm designer's prerogative, right? And then, no matter what, right, in some ways, I'm still saying there exists for all, right? So it's not like I'm right? So it's hard to say, is your answer wrong or right? But, I want to see, we're getting some meaning here, right? We're saying no matter what the input is, the number of lines of code is fixed and the answer is correct. Yeah?
Would it be the same thing as saying there's a specific number of k? There exists, right?
Yeah.
Saying for some number.
Yeah.
Don't we have to say there exists
Yeah.
a specific number of k?
Yeah. Yeah, the algorithm designer can build some algorithm with some number of lines of k. Are you saying something different than?
I don't know. To me, it doesn't seem clear that it's a specific, like there exists a k. It's not for all k. For me, when I read with some number k, I think of for all k.
I don't know. If I say for somebody in this room, they're going to get an A+. What would you get from that?
Hopefully everybody gets it.
Hopefully. But then I get in trouble. When I arrived here, I wanted to know what is the perfect mark distribution, and nobody would tell me. The only rules is I can't fail more than a third, and I can't give more than a third of you an A. Yeah.
You also say that there's an algorithm of finite length that for every input solves the problem.
Yeah, you could put in there the finite length. More details helps. Yeah. Now, I get a little nervous that if it sounds too much like there exists an algorithm and there exists an input, right? So I want to get some meaning out of there, and it's I don't know where the line draws the line, but I did say some algorithm, right? It gets to build an algorithm, it gets to build some algorithm. Yeah, I don't know. Just try to get some meaning here.
You're just adding verbs in front of the quantifiers that make it a sentence. So what's the essence of difference between there exists for every input and
This.
yours logic?
It's supposed to be the same.
Yes.
There's not supposed to be a difference. So I guess the question is, when you write something, the marker will have to decide whether the marker's convinced you understood it or whether you just copied the sentence out in words. It'll be a judgment call. But I have marked some of these, and when I say they're wrong, they were really wrong, right? They were really wrong. And you could really tell whether the person knew what was going on. Yeah?
For me, I thought of it like this. There's an unknown constant k and an unknown constant a that give us the right output for whatever variable input we give it.
Yeah. Yeah, it's sounding a little too much like you're just copying down the words, but yeah? Yes. Lines just tell you the number of lines of code in A for an input, right? A is our algorithm, K is an integer. People with me? You good? We want to go on to another one? Yeah?
Why doesn't the output depend on the input?
Where?
You say it says that no matter what the input is.
A will solve P. Here, the output does depend on the input. But the point is that it'll get you the right answer for P. Right? Yeah?
If we switch the A and P to place, we say there is the A and there is the A, then for all inputs, it will translate to the same meaning?
Yeah, you're switching the two exists. Yeah. It's good to know these various rules, that if you have a string of exists, it doesn't matter the order. In fact, I might even say there exists an A and a K. Right? It doesn't matter the order. And maybe the other order would have been more natural, because the algorithm designer is going to come up with the algorithm first, and then it's going to count the number of lines of K. Right? But I might be warming us up for other things. All right, so right here I changed their exists into a for all. So that's probably why I had the K first. Right? So now let's think about whether this is true. Right? So is it true that for every K, right, let's go here. A on input I has K things, right? Has K lines. And this says for every input, right? This says A has the same number of lines no matter what the input is. So that's still true, right? Now, if I have a particular thing about the game is adversary gives me a K, can I come up with an algorithm that always has K lines of code? Yes, right? Now, maybe you might argue, no, we're doing Java. And in Java, there's all this fluff that needs to be at the beginning and the end. And you can't have a one-line code of Java. But we're not doing that. Right? So, yeah. Saying it's true, the algorithm designer can build an algorithm with any number of lines of code. Right? You give me a K, I'm claiming I can build an algorithm that has K lines of code. Right? And then once I've built it with K lines of code, no matter what the input is, it's still going to have K lines of code. Right? Yeah?
If we put AI equal to PI, it will be false. Always.
You mean if we're going to do that. What is this set? Yeah? Yeah, that's the whole point. The point is I'm trying to come up with cool first-order logic statements. And so I want to be able to, this is saying what you're saying, right? This is saying that given an algorithm, the number of lines of code doesn't change with the input, right? And why did we put it there? So that I could say it, right? We're going to say harder things later. So this is an obvious thing. We're starting by saying obvious things, right? All right, so now it's slightly different, right? Now we're saying you give me an algorithm, right? This is talking about Ks. Every K has some algorithm, right? But it's also true that every algorithm has some K. It's not like some algorithms don't have a K. Every algorithm has some K, and when you run that K, when you run that algorithm, it has a fixed number of lines of code, no matter what the input is. Right, everybody buy that? So this is saying it's true. Each algorithm has a fixed number of lines of code that doesn't change with the input. Right? Everybody getting this? Right? Now, so I often forget who asked the question, right? Here's we're bringing in the problem in it again, right? Right? So here, what are we saying? Now, the algorithm, how many lines of code does it have, and does it solve the problem, right? And does it do that for every input? Is it true that for every K, there's an algorithm that does this? No, right? It's not true. right? Surely, given any problem, even if it's, given a reasonable problem, right? Given a reasonable problem, there's some minimal number of lines of code it needs in order to solve the problem, right? I mean, maybe there's some problem. Maybe we could say for all k greater than 1. We didn't. Well, I usually imply my values are greater. Remember when I say constant, greater than 0? I don't know. Anyway, you know that the intention of this is no, right? Now what do we say? What's this one say? Is this true? Okay, you guys fail. You all fail. You were supposed to remember I put toothpicks under your eyes and I fed you chemicals so you would react to this. Every input can't have its own algorithm. Right? So, this is true even for undecidable problems. Right? Undecidable problems. It's not a good statement because there should be a different algorithm for each input. Right? You can't have every input have its own algorithm. Yeah?
Wait, so it is true, but it's just not
Meaningful. Yeah. Yeah. So, I mean, what was the question? To say, is it true? And tell me something. What does this say about the world? And what you should say about the world is that if you wrote this down, you're an idiot. That's what it should say about the world. It's because this is just not a good thing to say. Right? For every input, you shouldn't have a different algorithm. Yeah?
What do you mean that it's also true for undecidable?
Well, remember the halting problem. We went through this, right? If P is the halting problem, then you give me an input. For that input, the halting problem is either yes or no, right? And so either the algorithm that always says yes or the algorithm that always says no will work, right? For every input, the answer is yes or no, and there's an algorithm that gives that answer, right? Remember this? So, see, that's the button that makes things not work again. I hate this button. I don't even, the truth is I don't even know which button it is. But I hit it all the time. Where are we? We're coming here. We're coming down here to computable with fixed resources. And then, which one are we on? That one. We did that one. Good. All right, so we did that one. Now what about this one? What is this one saying? Yeah, but you're just saying that. Give me meaning here. Here I want more meaning. Here I want more meaning. Take the complement of this. What's the complement of this? The complement of this is there exists an algorithm for every input it works, which means what? P is computable. Right? So what does this mean? This means P is not computable. Right? False. It's stating that P is not computable because no algorithm solves it for every input. Right? This is not computable. And the reason it's false is because if we go back to our first page, I said P is a computable problem. Right? Everybody good? And that was it. So that was an exam question. If I were to put it on the exam again, would you get it? Right? So this is the kind of thing, really, I'm really serious. It's this kind of understanding that we're going to be doing for the rest of this course. All right? And you might think that this course is so theoretical and useless, and I won't argue with you. All right? I've been arguing against this course since the first day they made me teach it, right? Probably even before that. I said, come on. Everybody in computer science should learn this, but not in second year. But nobody listens to me. All right, so we're going to do a little bit more. How much time do we got? We're almost there. 8 minutes? Excellent. We can finish these slides in 8 minutes. All right, so probabilistic algorithms. I don't know if we do probabilistic algorithms in this course, but I'm going to give it to you anyway. All right? So remember what computable means, right? Computable means there exists one algorithm that works for every input, right? And so we're talking about is the worst case. We're talking worst case. When we say a problem, the algorithm has n squared running time. We're talking about the worst case running time, right? That kind of stuff. All right, so it always gives the right answer. It always gives me it fast. Right here we're saying that the algorithm always, for every input, gets the right answer and gets it fast. Right? So I don't think I have it here, but let's do an example. Suppose I have n doors here, n meaning lots of doors, right? And I promised you that behind half of them are prizes, and behind that other half are bad things, right? Now we can ask, what is an algorithm now? Algorithm chooses which doors it's going to look in, right? And we can ask, what's the running time of this problem, right? Right? What's the input? The input tells me which doors have prizes behind them, right? The algorithm tells me which doors to look behind, right? So let's go back to this. How much time do you need to solve this problem? What's the postcondition? Is you find one prize, right? So what's the running time of this problem? Half of them have prizes. Half, right? In the worst case, I'd have to look at half of them, right? For every algorithm, no matter, right now the adversary knows which doors I look behind, right? And so the adversary gets to choose the input. And where is the adversary going to put those prizes? In the doors that you haven't looked in. So how many doors do you have to look in? You have to look at half of the doors, right? Everybody buy that? Now, does this seem fair to you? No, it's not fair, right? So what are we going to, and we're not now, we could then argue about a random input, right? We could say on a random, if you just put the prizes randomly, then I only have to look at expected 2 doors, right? Because each door has a probability half a success. But we don't care about random inputs because that scares us. We still want to say for every input, right? So instead what we're going to do is we're going to make the algorithm random, right? What the random algorithm going to do, it's going to look in a random door, right? And what's the advantage of looking in a random door? Is that the adversary doesn't, when he chooses the prizes, is going to know what your strategy is because he knows the algorithm but doesn't know your coin flips. So the adversary doesn't know which doors you're going to look behind. So let's write down the first order logic. We're going to say there exists an algorithm, right? And now what's this? It's a randomized algorithm, so it's going to take an input and it's going to take random bits, right? But the adversary has to come up with the input, knowing the algorithm, but not knowing the random bits, right? Does that make sense? So it knows, the adversary knows that you're going to look in random doors, but doesn't know which doors you're going to look at, right? So now, can we say that you always find a prize, right? Well, you've done it randomly, right? So quicksort is random, right? So if you have a random algorithm, he's saying I have a random algorithm that he claimed works, right? The adversary knows the algorithm but not the coin flips, and he has to choose Now he can choose a worst case input. But if he doesn't know which doors you're going to look in, all inputs are the same. Right? So, everybody follow that? Right? And so now, right, the coin flips are independent of the input. Now I randomly choose the coin. Oh, do we want, right now, do we want for all randoms or all coin flips? Maybe we want, there's two types of algorithms now, right? My algorithm could be keep looking in doors, random doors, until you find a prize, right? And I might have to look at all of them to find a prize, right? But in that case, I still know that no matter what the coin flips are, I'm going to get a prize, right? So this is saying, right, for every input, I might want the right answer, right? But we might say that your running time depends on the coin flips. And for some coin flips, the running time might be short, and for some it's long. And for the prize, what we just talked about here, the expected number of doors I have to look up will be only 2, right? And, right, or you could say, right, we could have expected time. We could also allow that sometimes you get the wrong answer. And we could talk about the probability that you get the right answer is, there's a bug here. We want the probability you get the wrong answer is exponentially small, right? And that's it. We're now done with first order logic slides. So next class, we're going to start with Turing machines.